Hello, I'm Joe Hamaker, and in this talk, I'll be discussing how to use something called the Rule of 166 to allocate space mission costs between development and first unit production costs, and between the spacecraft bus and the payload. First, a little bit about me. I'm the director of DoD and NASA programs at Gallerath Federal. I formerly directed costs for NASA, and I have over 40 years of experience with cost estimating and analysis. My contact information, my email address, is at the bottom of the chart, jhamaker@gallerath.com. Let's set some terminology conventions here. I'll be using the terms in bold, but in parentheses, I've listed some synonymous terms that you may be more familiar with. I'll be using the term space mission, also called space project or automated satellite. I'll be using the term development costs, sometimes called non-recurring cost, or DDT&E, or RDT&E. I'll be using the term first unit costs. That's the same thing as first unit production cost, or theoretical first unit, or T1. I'll be using percent new design, but sometimes that's called new design factor or heritage. Actually, the heritage is the reciprocal of percent new design. I'll be using spacecraft bus, or just the bus, or flight system or platform, or synonymous terms. I'll be using the word payload to mean instruments, or the instrument suite, or the mission equipment, or the sensors that are on board the spacecraft. So as a way of introduction, sometimes one has the total mission cost for a historical mission, for example, but it's not broken down any further. Let's say, for example, you found the cost in a Wikipedia article, but it's just a single lump sum. So if you want to use that to compare to some cost estimate you've done or some other purpose, it'd be very useful to be able to break that, to be able to estimate the breakdown of that cost a little further. For example, the NASA Instrument Cost Model version 9 is now capable of estimating production units. But to do that, you have to be able to tell the model the relative percentage of the first unit cost to development. So you can use this rule of 166 to do that. So the rule of 166 allows you to break down a cost into the payload. By the way, NASA calls that WBS 5, and the spacecraft bus, which is WBS 6 in the NASA WBS, and also break it between development and first unit cost. Now, the development first unit cost part of the heuristic is sensitive to percent new design, because obviously percent new design impacts the relative value between those two, between the development and first unit cost. You'll see that in a moment. So where did this rule of 166 come from? Well, I developed this rule many years ago, I think in the mid-1990s, and it's held up well, actually surprisingly. I just checked it against 24 recent missions, and it seems to still be correct within single-digit percentages. And it also checks well with the paper written by the Gallerath chief scientist, Dr. Christian Smart, and a co-author, Gail Reese, back in 2008. Now, I say I'm surprised by the fact that it's held up, because the lore on the street is that spacecraft buses are becoming commodity buys. So if that were the case, you would see the percentage for spacecraft buses going down relative to the percentage for instruments. But I'm really not seeing that in the data, and I'll show you that in just a moment. All right, so here is the rule of 166 implemented in a very simple Excel spreadsheet. A screenshot of that is in the top left-hand corner. Now, the initial state for the rule of 166 is to assume 100% new design for the payload and 100% new design for the spacecraft bus, shown in the green cells there. So if you do that, the rule of 166 allocates or assigns 100 units of money to the development cost of the spacecraft bus. That's an arbitrary assumption, but that allows you to get a ratio for everything else. So the rule of 166 says, okay, the spacecraft bus development cost is 100 units of money. Now, the data I had at the time said that about 22% of the development cost was associated with the first unit production costs. That's where the 22 comes from. The data at the time said that usually about a third of the mission cost is associated with the payload development. So that's where the 33 comes from relative to the 100. And finally, the data I had at the time said that the production cost, first unit production cost of the instruments, or the payloads, was about a third of the development cost. That's where the 11 comes from, 1/3 of 33. So in this construct, you see the total in the bottom right-hand corner is 166. So thus the name rule 166. Now, if you make other assumptions about the percent new development, obviously the math changes just a little bit. For example, if you use 80% new design for payload and 60% new design for the bus, showing the top right-hand table, the bottom right-hand corner becomes 119. So you can call it the rule of 119 in that case, but for convenience, I continue to call it the rule of 166. By the way, the 80% and 60% is what I find to be rather typical of the new design for payloads and spacecraft today. They always start out lower in proposal stages and early conceptual development. We believe that our payload is going to be more off the shelf, more heritage, somewhat less, or maybe even a lot less than 80%. We also convince ourselves that the spacecraft bus is going to be more off the shelf, but it ends up being more like a 60% new design, typically looking back for the bus and maybe 80% for the payload. But you can enter whatever you want into those cells, and the rule of 166 will churn out the arithmetic to split the cost. So if you'd like the simple Excel spreadsheet, email me at my jhammaker@galrath.com email address. Now, trivial suggestion on use, but this comes in handy. When you try to use the rule of 166, if you'll enter the fractions into your Excel spreadsheet, for example, say you have a total cost out of Wikipedia, again, a total cost for mission, and you really would like to know, I wonder how much of that cost was attributable to the payload development. Oh, I'll use the rule of 166. Well, if you'll type in that fraction, 33 over 166, instead of doing it offline on your calculator or otherwise, you'll type that fraction into your Excel spreadsheet. Then a month later or 2 months later, when you're trying to remember, where did I get that number? You'll see the fraction and you'll think, oh yeah, I used that rule of 166. Okay, so I've tried to corroborate this with 24 recent space missions. Now, actually, I can only corroborate this spacecraft bus payload split. That's the only thing I could check because none of these 24 missions actually gave the development costs and first unit costs as separate entities. They're mixed together or added together. That's because in a one-off spacecraft development program, the developers don't normally think of non-recurring or recurring costs separately. So I could check the spacecraft bus split with these 24 missions, but not the other. So the data from the 24 missions is shown in the table there. For example, the mission one had 72% of the costs associated with the bus and 28% associated with payload. All the rest are given there, and on average, they averaged to 71% for the spacecraft bus and 29% for the payload. Now, if I just use the rule of 166, shown in the second table there, you've seen that before, and if I'd used the 100% new design, I would have gotten 73% and 27% for those two numbers. Well, that's very close to what the actual data is showing up to be. If I modify it to be 80% new design for the payload and 60% new design for the bus, I would have gotten slightly different percentages, as you see on this chart, 69 and 31% respectively, but that's still real close to what the actual split is on the 24 missions. Notice that 2/3 of the missions I've rated green here with a green smiley face, and 3 or 4 or 5 of the missions are yellow because they weren't all that close. The rule of 166 wasn't all that close to the reported data. And then 2 of the missions were significantly off, so I rated those as red. But 2/3 of the 24 missions are green, so that says that they agreed fairly well with the rule of 166. Now, the last 5 missions on the chart are small sats, and notice that 3 of those 5 are also green. So the rule is holding up even for small sats more often than not. The second way I checked the rule of 166 is I went to the paper I've previously mentioned. I've referenced it here. The reference is in the bottom right-hand corner of the chart, the Christian Smart Gallery's paper. And they have a table in that paper that I've modified here. I've reproduced the table on this chart, not directly from their paper, but the numbers are all the same. I just changed it to be different terminology and I laid it out a little bit differently to try to explain, compare it to the rule of 166. So they had 5 categories of heritage, as you can see here, from 100% new design down to existing drawings. And for each of those, they assigned a percent new design shown in column B. Then in column C and D, they reported out the percent for development and first unit cost. And for example, for 100% new design, it was 77% for development and it's 23% for first unit. And then you see the rest of the numbers there for the other categories of heritage. I came along in column E and said, hey, I want to use the very same percent new design numbers they've used. So I repeated those. I repeated column B and column E. And then I used the rule of 166, and I'm showing the math there in columns F and G to calculate what percent the rule would throw to development and what percent it would throw to first unit cost. And then I rated over on the right, in the far right column H, are they close or not? And you can see that the first three were real close. I'm getting about the same within a small accuracy bar, error bar, the same as what the data was in the Smart Reese paper. It deviates a little bit for moderate modifications and then deviates more severely for existing drawings. But for three of the categories, at least, the rule of 166 is pretty consistent with their paper. So in conclusion, I developed the rule of 166 decades ago, but it's held up well, checking against these 24 missions, as you've seen. So if you're in a pinch and need to fracture the total cost of a space mission into development cost and first unit cost, you can use this rule of 166 to do that. Or alternately, you might look up that excellent Christian Smart Gail Reese paper, because the subject of their paper is actually using a beta distribution to allocate cost and development first unit cost. I didn't talk about it here. You can see that in their paper. I only wanted to harvest their historical data, which I showed you back on chart 8, to compare it to the rule of 166. So if you have any questions about this or comments, or you want me to send you the simple little spreadsheet that implements this rule, again, just email me at jhammaker@galworth.com. Okay, thank you very much.